What we're going to do is some activities. Some can be considered a demonstration, but these are actually quantifiable. Students can do these as a lab activity. We have some write-ups to support that, but we are going to be doing standing waves in an air column.
Ah, okay, because we just saw standing waves.
That's correct.
Brett was just demonstrating them, and now we're going to be using that same concept, looking at standing waves, but you're going to be using it within this nice column here, correct?
That is correct.
I can't wait to see it.
All right. So let me just check with Nolan. Is my screen okay? Perfect. So this is PASCO's resonance air column, and it may not seem like much. It's a plastic tube, right? That's got these convenient stands on it to keep it elevated off the table, and then there's a slidable plunger in here. But what I've discovered is, after trying to do these activities and these demonstrations with other setups, giant tubes. I remember at one point I was using the old tube that the tracks would ship in, right? They work well. This works amazing. And it works amazing for audible frequencies that we would have in our classroom, not so much, those really low frequencies or really high frequencies, although it can do that. It's an amazing tool for exploring how sound waves behave in an air column. And in this case, with the plunger in place, this is a open-closed air column. One end is open, one end is closed. But we could remove the plunger entirely, and this could be an open-open air column. And I mean, I've got pieces of PVC that can help me do open-open as well. And I'll show you at the end of this just something neat that I was shown some time ago that just absolutely, I had never seen it before. It's something so simple, and so I'll explain in just a second. But what we're going to do with our students is we're going to give them tuning forks, right? And so these tuning forks will produce sound waves. And they produce a sound wave at a fixed frequency, which is written on here. This one says 320. Let's see if we can go a little bit higher. Here's 341. And so sound waves are going to be generated. And if you hold this tuning fork near the open end of this pipe, those sound waves are driven down the pipe. And now what we want our students to sort of discover is that at the right length of pipe, this system starts making a louder sound. You start hearing a louder sound, and then we'll call that resonance. It starts to resonate. And what's actually happening is those sound waves are being reflected back, and when the speed and frequency and length are just right, you get standing waves established in the pipe. It's just like we saw on the string. And when those standing waves are, when those standing waves are established, this system starts to make, the whole thing starts to make sound louder than you would hear with just this tuning fork. In fact, if I strike this tuning fork, you probably can't hear it. I mean, tell me if I'm correct, Nolan, if I hold it a little closer, you can hear it there, right? But out here, we can't hear this. And in fact, when I hold it over the tube, we can't hear anything either, right? Because I remember I said the resonance is a combination of lots of things, including pipe length. And so Dan is going to help me. So I'm going to strike that tuning fork, and as he draws the plunger out, keep going. Right there. And so I'm going to do that again. I'm going to strike this tuning fork, and then Dan, you can go back and forth at that location. And you can hear the sound. Now you can hear the sound. We can hear the sound in the room, right? And teachers love this when every group is going at the same time, right? And so what we've done is we've found a length of pipe where a standing wave is established. And now this, like I said at the beginning, the system is open-closed, right? And so there are boundary conditions that those waves have to meet. And one of them is that standing wave at the closed end of the pipe, what we have here is a node, right? And at the open end, we have an antinode. And if we had had open, we would have had an antinode and an antinode at this end, right? Now that's a pretty general condition, right? Because we didn't talk about anything in between the antinodes or anything in between that node and antinode. So what happens if we draw this plunger out even further? Goes quiet, still quiet, and then keep going. Keep going. Right there. we find another location where all of a sudden this tube, this just air column, starts making more noise. So what's going on here? Well, this tube setup where it was closed and open, the standing wave that gets generated in there has to have a node and an antinode, and so that can happen when there's only 1/4 of a wavelength in there. But we just found another location where it happened again. So what's going on? You have to have a node and an antinode. So does that mean we've added a whole nother half of a wavelength? Because in between there, we wouldn't meet that condition again. So we must have. So here, this sound wave that's in there has to be experiencing a standing wave where there is a node, antinode, and there has to be now a half a wavelength in between, a new half wavelength, right? And if we know how fast sound waves travel, right, and we know the frequency that we're generating, we can calculate what the wavelength is, right? And so we can compare the calculated wavelength to what we have just experimentally determined. So this is not quite one wavelength, but it's 1/4 plus a half a wavelength. So there's 3/4 of a wavelength in here, right? And we could keep going. And obviously, eventually, we're going to run out of room, right? But we can do different frequencies. So this is 512 hertz. And so, keep going. Right there. And so clearly, we could tell using our ears, this is where we're resonating, right? Look how much shorter that distance is than the first one. And so if we keep going, right there. And so we had the same thing happen. Now we've got 3/4 of a wavelength, but look how much shorter the length of tube is. And as Dan popped off, there are clips that come with this system, and they snap right on the tube to help you mark where different things are happening, right? And so we can take these clips, and so with the plunger in this position, we had resonance. We can snap a little clip on there, and students can take their meter stick and they can measure the length from the end of the pipe to the plunger, 49 centimeters. And we know 49 centimeters is equal to 3/4 of one wavelength. And we could keep going, right? Because this is about what we added, that half wavelength. We could add another half of a wavelength and keep going and still meet those boundary conditions. Now, tuning forks are nice. They're very convenient, found in nearly every physics classroom on the planet, right? But I'm constantly hammering this and trying to find it. It can be difficult sometimes. Also, I want to point out, a standard tuning fork like this, if you strike it hard enough or on a hard surface, you will get overtones. You will get frequencies that are not the one that you care about. What I've found is for tuning forks like this one, if you grab it instead of by the handle here, but just at the base of the forks, the tines, and you strike it right in the middle, you can avoid those higher frequencies. Just a tip. So what we can do instead is PASCO has this little mini speaker that's designed to fit right there on the end of the tube. And this can be driven by any function generator. This one is just PASCO's digital function generator, right? And we can generate constant pure tones using a sine wave, which is exactly what this does. So it's at 1,000 right now. This was 512 hertz. So what do we suspect the length of pipe will be at the very first? Probably shorter, right? So let me turn this up. Right there. See, it's much louder. Now draw it back just a little bit. Much quieter, right? You can barely hear it. And so right there, look at the length of pipe is much shorter. In fact, it's about half as short as the 512 hertz tuning fork. And as Dan keeps drawing it back, he finds more and more. Because remember, every time we add half a wavelength, we're going to be at resonance again. We're going to meet those boundary conditions. We can even play music with it. And so we've been using our ears. Let me turn this down. We've been using our ears to sort of determine where to stop drawing the plunger out. We could take that a step further. I'm going to go over here. And we can use something like a sound sensor. So this is PASCO's wireless sound sensor, right? And let me get my computer up. And so we can use the wireless sound sensor to measure sound level data. We can actually quantify how loud it is, right? It gets louder when it's resonating. This is the tool that we can use to help us figure that out. And now it's mounted to the smart cart, which I'll explain more about in just a second. So stay tuned for that. And so I'm going to open a file that I have saved on here called air column. And in this file, I've got to connect my sensors real fast. So I should probably turn them on. So sound, smart cart, I'll just connect that now. We're not going to use it. And so I've got a graph of sound level versus time. So I'm actually going to move this back just a little bit. So I'm going to turn this on. Actually, I'm going to reduce it back down to probably about 340. So I'm going to turn the frequency down to 340. There's 348. All right. I'll move that a little bit closer. Yeah, and so now what I'm going to do is I'm going to click record, and we're going to do this while I'm talking because it's going to pick up my voice, but we see the sound level, and Dan's going to move the plunger, and I'm going to watch this graph, and I'm going to tell him right where to stop because it's going to be the loudest, the point where the graph is the highest. Okay, ready? Go ahead. Oop, go back. Right there. Turn that off. And you can see I stopped him right in my graph area here where we were at about 65 dB, right? Everything else was sitting at about maybe about 62, 63 dB. So when the sound level is the greatest, that's where we stop. So students can actually be much more technical in terms of this application, really fine-tune where the plunger should stop so we can get resonance. And so that's, the main application, but I just wanted to show everybody one other thing too, one other neat thing that I've been sort of playing around with. I'm going to move the speaker a little bit closer. And so the reason I have the sound sensor attached to the smart cart is because, Dan, do you mind grabbing that track for me, please? I can take this smart cart and actually measure the sound level. And so in a sound wave, in a standing sound wave, we get areas of compression and rarefaction, right? Where areas are higher pressure compared to others. And it's vibrating. And so we can actually get physical movement of this tube, right? Where the sound is technically higher above the tube. Now, we may have seen a Rubens tube, right, where it's got holes in the top of it and little flames, and the areas of higher pressure will push gas. Let's say you've got propane in it, will push the gas out higher and you'll get taller flames. This is kind of like that, but with the sound sensor instead. So you don't have to have burning stuff in your classroom, even though burning stuff can be fun.
Disclaimer, we don't burn stuff in our classroom.
We don't burn stuff. So let me get rid of that. And Dan, do you mind drawing that plunger out for me? Till the face of it, keep going right there. Well, forward a little bit. Right, so this flush with that marker. There, perfect. And so I have this marked ahead of time. And I'm going to turn my frequency generator back on since I just turned it off, up to 2400 hertz, which is really noisy. Not a friendly sound. But what I'm going to do is this length of tube corresponds to a length at which we get standing waves established in there. And like I said, I figured this out ahead of time, but we get several areas of nodes and antinodes. And what I'm going to do is measure the sound level while simultaneously moving the sensor along the length of the tube. And in my graph, I'll plot sound level versus position. My smart cart, I accidentally turned it off too. Me and my fumble fingers. Let me just turn that back on. And so we can get a graph of sound level versus position. And so we can tell where the areas where the antinodes are in the tube, how far apart the antinodes and nodes are. Right? And so it's got to be quiet when we do this. There's a bit of a fan above me. We'll try it. We'll see what happens. But I'm going to click start. Actually, I'm going to turn this on first. We'll get some sound going, establish the standing waves, and then I'll record data as I move that cart. So here we go. And there you go. And so on my graph, you can see very clearly there in about the first half of the graph, the left-hand half of the graph, there are 3 very distinct bumps in the graph. And those represent antinodes along this tube. And it was right about in this section. Now, I got a little flat in the later sections, right? And that just could be, spatial constraints of the tube. I didn't spend a whole lot of time setting it up very accurately. But what we could do is we could take our tools inside our software now, and we can figure out exactly how long one wavelength is, right? And so in a standing wave, one wavelength, you're going to see 2 antinodes, right, and 3 nodes. And so this is telling me that we've got a wavelength of about, bless you.
Thank you.
We've got a wavelength of about 16 centimeters. And so if I do the math, 2400 hertz, 344 meters per second, we know the speed of sound, we know the frequency, we can figure out, we can calculate what the wavelength is, and it's about 15 centimeters. So we're very close. And we could have redone this and tested it in different areas as well. So
You're so excited about these waves.
Yes.
I mean, you're really so very excited about these waves. But this is again, one of those things, you kind of started with waves, we're back in waves. This is one of those things that we teach every year, we teach at every level, and yet we always struggle trying to show these things, and now you're showing them very easily.
Yeah.
Really, with some very nice stuff. Are these labs available if folks wanted to look this stuff up? What can they find?
So the labs with the resonance air column, we have both advanced physics applications for it. So if you go to our AP physics manual, advanced physics 2 manual, sound is in there. We also have on the resonance air column webpage, the product webpage on PASCO.com, there's all kinds of activities in there as well, including ones with the frequency generator and with tuning forks.
Oh, that's awesome.
Yeah.
So you saw it here, but you can do it there. All you got to do is go to PASCO.com, download some of our labs. Are there any videos of this?
There is now.
That's right, because this has been recorded. So we will have these videos for you. You'll have access to this. You can watch all of this and all the labs that JJ's put together. So ladies and gentlemen, Mr. JJ Plank.
Thank you very much.